Okay, so this module is going to be a little bit different. We're just going to step through the ion configuration files for the base scenario. So again, this is the scenario that has the satellite that just moves in and out of connectivity with the rest of the ground infrastructure. Sort of these are the things that we're going to run through. We'll talk about what's in each of these the files with these kinds of files extensions, and the stuff to the right lists what's sort of going on in that file. So in like the ionrc file is talking about, okay, we talked before about node numbers and service numbers in the IPN naming scheme. So the ionrc file says, okay, what's your node number? And talks about identifies the ion config file that you're going to use for configuration parameters. Those parameters are things like how, in particular, the important one is how the simple data recorder is configured, and that has to do with things like, are we going to use transaction reversibility? Are we going to back the SDR in a file or run it only in memory? The scenarios that are in the dev kit, I think, are probably all just run the SDR out of memory. It's faster that way. It's not robust against being shut down at arbitrary times, but we're not looking for that in just the simple scenarios that we're running. The bprc file talks about what forwarding schemes are going to be used. We're going to be using exclusively the IPN scheme that names things as IPN:number.number. bprc file also talks about what convergence layer protocols are used. So these are the protocols that are used underneath BP in order to move bundles from router to router. And what endpoints a node is a member of. If you remember, we talked before briefly about needing to identify the endpoints that a node was a member of, so that, for instance, when we did a ping command in the previous module where we were looking at scenario 2A under constant, we did a ping from IPN 1.3 to IPN 2.1. The .3 there identifies the service number, so that that node number 1 is a member of 1.3, and that needs to be configured in the bprc file or done sort of programmatically. The IPNRC file talks about mechanisms to reach your immediate neighbors. LTPRC has LTP configuration stuff. There's probably a whole there's a lot of stuff that sort of sits behind LTP configuration. You would think that LTP would be extremely simple in that in what it does, and it is. However, getting LTP set up right for high performance in sort of the environment that you're looking for can be a bit tricky. There's an Excel spreadsheet that comes that ships with the ion distribution that will walk you through a little bit about how to set up the various parameters in LTP in order to try to get good performance. The issue is really one of resources and resource allocation. LTP is going to need to is going to need to be able to hold on to things for in order to retransmit them. And it plays into sort of the overall storage scheme of the node. There's some stuff called zero copy objects that Scott will talk about in the lecture notes that mitigate the sort of the space requirements for doing all that. But still, there's some bookkeeping that has to go on, and getting those numbers right can be a little bit tricky. We don't do anything with ion security here. We're using just the open source version of ion, so it doesn't include a security protocol implementation in it. We can talk a little bit about ACSRC aggregate custody signaling. This is a capability that was developed by some of the folks at Colorado University who were flying experiments on board station, and their problem was that they had a relatively high rate downlink in the megabits or tens of megabits, but their uplink, because they were sharing that uplink with sort of a lot of the payloads on station. By the time you divvied it all out, their uplink rate was on the order of like 8 to 10 bits per second. And so if you do that, then you really have trouble acknowledging anything if you want to send data reliably, and they did. They wanted to send data reliably down from their experiments on station and get it either acknowledged by the ground or have it get retransmitted retransmitted. Their solution was and normally the way that would happen in bundle protocol with custody acknowledgments is that bundles that needed reliable delivery would be marked as requesting custody transfer, and then at each node in the network, that node would take custody of the bundle and accept custody from the previous custodian, and in that manner move that point of retransmission towards the destination until the bundle got to the destination. The problem with that is a custody acknowledgement for a bundle is not a heavyweight thing, but it's several tens of bytes. And if you're sending down hundreds of bundles per second and your uplink rate is on the order of 8 to 10 bits per second, well, you really just can't acknowledge all of those. So what the Colorado University folks did was to develop a mechanism that is a combination of a bundle extension block and run length encoding mechanism of acknowledgements. So the extension block is put on by the sender of bundles that want to use this aggregate custody signaling, and aggregate custody signaling really is a link layer thing. It wants to run across a single link, as opposed to the regular bundle protocol custody signaling. Typically would run. Typically bundles would be acknowledged, at each link in the path, but not necessarily, right? So that you could have cases in bundle protocol where a bundle was requesting custody transfer, got to a node that could not take custody of it for whatever reason, but might be able to forward it, and then the next node to receive that bundle, if it wanted to take custody, would have to figure out who the current custodian was from the primary header and send an acknowledgement back, and it would be sort of a multi-hop custody acknowledgement, not link by link. But this aggregate custody signaling is really designed to be link by link, so that in particular the source can put on can associate with each bundle a sequence number, and that sequence number is different from, say, the timestamp creation, the creation timestamp of a bundle, because the creation timestamps for bundles are not they're not compact. If you receive a bunch of bundles, you don't really have any way of knowing that you've gotten all of them just from looking at the creation timestamps. So what aggregate custody signaling does is it associates sort of real compact sequence numbers with bundles that it's transmitting, and then at the receiver can build these run length encoded kinds of acknowledgments that say things like, I've received bundles 1 through 300, instead of acknowledging each one individually. And so you can save a lot of bandwidth that way, and that's how they got around their problem of having low uplink bandwidth. And CFD-PRC is for configuring CCSDS file delivery protocol parameters. I think I've got an example later that actually uses CFDP to move some files around, and we can look at how that works. So I'm going to do this in slides, and if you want to follow along from a terminal window, if you just get into the directory where the config files for the base scenario live, and so that would be like ~.core/configs, and then NASA_DTN_dev_kit base/config, and then open up. We'll start with the ionrc file, and you can use VI or gedit or the editor of your choice. I don't think Emacs comes in pre-installed with the dev kit, but you could certainly put it on there. So in the ion config file, and we're looking here at just node 1, and so this is a config file that was generated, I think, by a configuration tool that JPL puts out that they are right now updating for the latest version of Ion. But it does a nice job of actually not just putting out sort of sets of config files for entire configurations, but also commenting those reasonably well. So this is initializing Ion node number is 1, and we're going to use this Ion config file. And so a lot of the Ion admin programs sort of follow this kind of convention where there's an initialization or start command that is typically a 1, and then maybe some parameters to it. And then down at the end, there's another command that actually says, okay, now make it, start running all the processes that we've talked about in this, and that gets called with an S. I also put in the slide deck, if you're following along with that, there's this sort of blue star down here. If you click on that, it'll just take you down here, and I put in the man page for IPNRC. So the format is 1, and then a node number, and then an optional Ion config file name, and this will tell you sort of how that all works out. The man pages are a wonderful resource for if you get stuck in trying to get a configuration to work and something isn't working. The man pages are typically kept up to date, and they'll help you out there. So that's that. This is the Ion config, N1's Ion config file that got referenced there from the INRC. So this has got some stuff that's mostly associated with, I think actually all of it is associated with the simple data recorder. So there's a key for the working memory. There's a name for the SDR, and then there's a size of the working memory, and all of this is going to get allocated one time when Ion starts up, and after that Ion doesn't do any dynamic memory allocation. This was as a constraint of lots of flight software has this constraint that they don't want people doing dynamic memory allocation in the middle of their programs. So Ion mallocs a giant chunk of memory into this simple data recorder, and then manages all of it internally. And Scott talks in some of his slides about how that's all managed. The config flags line here talks about configuration of the SDR, and that really has to do with these items down here. So the config flags is just a logical OR of these 4 flags. So SDR in memory, SDR in a file, SDR reversible, SDR bounded. In a memory means that the SDR is kept in memory. SDR in file means it is kept in a file. If you set both of those, it will keep it in both memory and a file. So it'll do the writes and then write through to a file so that it's persistent. Reversible is actually implementing transactions within the SDR, so that if something goes horribly wrong, then everything there's a little journal that gets written in there, and if things go horribly wrong, like the machine gets power cycled in the middle of one of these transactions, you can back out to the beginning of that transaction, and then everything will at least you'll lose what happened during the transaction, but everything will at least be in a consistent state at that point, so that you don't lose all of the SDR and all of the state that you have. And SDR bounded has to do with some internal error checking that the SDR code will do to make sure that nothing is going out of bounds while you're running. So in this config, I've just set the config flag as just 1, which means SDR in memory, nothing else. And that's really for performance. There's also this heap words down here is another memory allocation command. So this is the number of words for non-volatile storage. So the working memory is stuff that Ion is going to be using sort of as scratch memory, and these non-volatile storage is stuff that will be managed out of the SDR, and then the path name to get into where the journal is stored. bprc, again, like a lot of these things, there's an initialization command, 1. And here we talk about what are the forwarding schemes that we're going to use. Again, all of the scenarios that we're going to use in both the dev kit and the class materials are all using this IPNFW, and it is associated with an IPN admin endpoint. The other schemes that are around are, there's a DTN forwarder that Ion implements that uses the DTN naming scheme. The DTN naming scheme is the sort of the original, one of the original naming schemes that came out of RFC 5050, and in particular the DTN2 implementation of bundle protocol. And so it uses things that look much more like a host name and then some string instead of a service number. So the DTN naming scheme would be something like DTN : / and then instead of a node number, there would be a string that maps into a host name, and then instead of a service number, there would be some sort of other string that mapped into sort of what that service is. The bprc file talks about how we're going to talk to our neighbors. So in particular, here are a couple of lines that talk about we're going to be using TCP protocol, and these numbers off to the right are sort of the nominal payload and the nominal overhead size for bundles that you're going to send using that protocol. So those are used by Ion when it's doing some, in particular by schedule-aware bundle routing, when it's doing some of its routing calculations to try to figure out when a particular link is going to become full. So it'll look and say, okay, I've got a megabyte. How many TCP segments is that going to be? How many of that is going to how much of that is going to end up being overhead? And eventually it'll fill up. If the contact is short enough and the data rate is low enough, then schedule-aware bundle routing will figure out that it will eventually consume all of that contact, and then it will start scheduling. If you have fragmentation turned on, it would then fragment the bundle and start scheduling fragments to go out along a different path, or a different contact at least. More of bprc, talk about inducts and outducts. So we talked before, back up here, we were just saying, look, there's going to be a thing called TCP, and these are the overheads. There's going to be a UDP and an LTP, and these are the overheads. Here we're getting more into, okay, how am I actually going to be sending and receiving using these protocols? So this says I'm going to instantiate an induct for TCP. Inducts are receiving ducts. I'm going to receive, I'm going to bind that to 0000, which in the IP world means any interface. Bundles that come in on port 4556 to any one of my interfaces, I'm going to give them to this TCP CLI process, and that's going to handle getting the bundles out of the TCP connections and giving them up to the bundle protocol layer. Similarly, I can do the same thing for UDP, so I'm going to add an induct for UDP. It's going to be listening on IONAT or any, so any interface. Again, port 4556, IP is okay with that. You can have multiple protocols that are sitting on the same port, and it will sort that out. So there's TCP and UDP that are both on 4556. And the UDP packets it's going to give to this UDP CLI, so this is the UDP convergence layer input. And there's also an induct here for LTP. And here it says this is LTP, and stuff that is headed for LTP engine number 1 give to the LTP CLI. And later we'll talk about the LTP-RC file, and that's the thing that's going to have the other bit of configuration that binds LTP engine number 1 to UDP interface and port 1113 on that interface. Similarly to the inducts, we can instantiate a bunch of outducts. Here it says there's going to be an outduct to 127.0.0.1, so this is loopback. In most of the things, most of the configurations that I build, I will build a UDP convergence layer sitting on top of loopback, mainly so that I can ping from a node, I can ping itself and just make sure that ION is up and running and that I've got everything else set up right. So this is a UDP CLO, UDP convergence layer output that's sitting on top of, it's going to spit out to 127.0.0.1, and it's going to go to the default port, which is 4556. And this UDP CLO2, the 2 here is what ION should assume is the round trip time of that link. And it's going to use that to figure out if you have bundles that are that request custody transfer. That's going to be it's going to use that too to compute the timeout value for when it should retransmit if it doesn't receive a custody acknowledgement for those bundles. So we've got this UDP convergence layer for loopback. We've got another one that's headed for 10.0.0.2 on port 556, and again we just gave it a 2-second, asserted that it had a 2-second round trip time. And finally there's an outduct for TCP that's headed for 10.0.2.2 on 4556, and the TCP outducts are actually the program to use here is just null. It's 2 single ticks. The TCP outduct is actually serviced by the induct process that's sitting up here. So you don't need you don't need to have a program here to handle the stuff that's going out, but you do need to tell it that there is no program. So the sort of the way to understand this is setting up a UDP outduct for 10.0.0.2 port 4556, and when you want to send bundles there, you give them to this UDP CLO process. More of bprc. We talked a little bit earlier about watch characters. When you run bping, you'll see a bunch of A's that go out. This is going to set the level of the watch characters that are going to be generated. And we'll talk later about what all those mean, and we'll go through a set of how to turn those on and where to look for them in core. As part of when core starts up and starts all of the ION processes, it pipes a lot of the output into a couple of files, and that's where we're going to go look for eventually for the watch characters to show up. From within here, we can one of the things that we can do from within the bprc file is actually run another config file. So here we're going to run the IPN admin program on n1.ipnrc, and we do that so that by the time we get down here and start all the schemes and protocols, this is going to load in the rest of the stuff that we need to load, and then when we start, we'll have everything up and running the way we want. IPNRC is going to talk about how to get to your neighbors. So these are the various plans. So we have 3 plans here. plan to get to nodes 1, 2, and 3. We're node 1, so our plan to get to ourselves is to use UDP and to go to 127.0.0.1 and the default port for that, which is 4556. We've got a plan to get to node 2, and this is UDP 10.0.0.2 4556, and a plan to get to node, or sorry, UDP as well, plan to get to node 3 via TCP and 10.0.2.2 4556. So these are how to get to your immediate neighbors. This doesn't have anything to do with sort of multi-hop communication. So this only lists the nodes for which we have direct connectivity via some convergence layer. And then this is the LTPRC file. It's got sort of the same kind of notion. There's an initialization command. There's a start command down here that's going to start the UDP link service input. So this is the part that is listening on, again, IPNRC and port 1113. And in the middle, we define a set of spans. So that with a span is a communication opportunity for LTP. So this is saying that we're going to add a span to node 4. And we're going to, when we want to invoke that in order to send bundles, we're going to use UDP LSO, the UDP link service output, for 10.331, and then this is, I think, a nominal data rate. I'll go back in here to the man page and pull that up and say, okay, so this is add a span to a peer engine number. There's a max export sessions, a max import sessions, a segment size, an aggregation size limit, and a time limit. So this is a span to node 4. We're going to run a maximum of 100 concurrent input and output LTP sessions, and we do that because we may want to, each LTP session is going to be handling one LTP block, which for our purposes right now, think of as a bundle. There's other ways to get multiple bundles into a single LTP block, which you might want to do for other efficiency reasons, things that are similar to why you would want to use aggregate custody signaling. But for now, think of one LTP block as one bundle, and so if we have a particular packet loss rate, and if we only ran one LTP LTP session at a time, then we would have to wait for that entire LTP session to complete correctly before we could send the next bundle. And we don't want to do that. We want to be able to send multiple bundles in parallel if we can, and that way, when one span is held up because it's lost a particular LTP segment and has to retransmit, the other spans can keep going during that time, and we'll get full link utilization out of it. And so this the 101 out here. See what were these? This is max export, max input, the maximum segment size, and then the size and the time limit. So the maximum segment size that we're going to send is 64K because we're going to be sending LTP over a UDP LSI, and we need to fit into a 64K UDP datagram. And then the maximum size and the maximum time here, LTP can, as a way to increase efficiency, you can aggregate lots of small, you might want to aggregate lots of small blocks or bundles into a single LTP transmission so that LTP does its reliability at the block layer. So you can aggregate a lot of you can aggregate several small bundles into a single LTP block and ship them across the link and get the LTP level acknowledgement just once for all of those. So what this says is if you're sending fewer than 100, if your LTP block is smaller than 100 bytes, and or you have been waiting less than a second, then keep aggregating. So this typically will spit out LTP blocks relatively quickly, because the 1 second aggregation means if you haven't gotten, if the LTP block size is larger than 100 bytes, which most of them will be, send immediately. If you've been waiting more than a second, send immediately. So this typically ends up with essentially one bundle per LTP block. And then again, LTP has its own watch characters. So this is telling it no watch characters. And again, we'll talk more about that later. ionrc, we're not going to be using ion security, as I said before. However, you do have to, it helps to have an ionrc file that simply says to initialize the security infrastructure, and then you can do whatever you want about echoing stuff. But if you, the rationale here is if you don't, then Ion will sort of continually complain into the log file that it has no configuration for IonSec, and it's not happy about that. And all that does is clogs up the log file with a bunch of stuff that you then, if you're looking for, if you're not doing anything else with it, it just fills up disk space. If you are doing something with it and trying to comb through the log file and figure out what's going on, then you just have to ignore all the IonSec warnings. This is the aggregate custody signaling configuration. So we talk here. This is again initialization command, and then a logging level. So you can log, errors, warnings, info, and debug information. So here we're going to log everything below debug, and then a number of heap words. ACS aggregate custody signaling does its own, gets its own sort of instance of a simple data recorder using the same mechanisms that the rest of Ion uses, but in its own private space. And so it's allocating its own memory there in order to use that. Order of execution for the DevKit scenario. So this gets a little bit into the sort of the magic behind causing the scenarios to fire up and actually run Ion. So the order of execution here, first is the ionrc file, then ionsekrc, then LTP, and bprc, which will then run the IPNRC file, and finally CFD-PRC. And I think most of them I've now added an aggregate custody signaling configuration to as well, so that that'll get run. If it's defined and present, it'll get run, and if it's not, then I think it just gets ignored. So as an exercise, in the base scenario, the trick is going to be to change the UDP link between nodes 1 and 2 to use TCP in the node 1 to node 2 direction, and we can leave it alone in the other direction. And in fact, it's slightly informative to do that, just to drive home the fact that the convergence layers really are unidirectional. You can use TCP in one direction and UDP in the other direction. In order to use TCP in one direction, you'll need to have bidirectional connectivity at the IP layer, because the TCP acknowledgments need to get back. But fundamentally, you can use different convergence layers in different directions. We talked about this a little bit before as well. You can run the various Ion admin programs interactively. They've all got command lines, and typically an H and maybe even a question mark at one of the command line prompts will give you a whole bunch of useful information about what and how what you can do with that admin program and how to invoke it. So we could make these changes actually to a running node by using the command line interface. We're going to do some. We'll do some work with the command line interface later. But for now, I think what we'll try to do is just get everything running in by changing the config files. That way, if things don't work, you can stop and restart and sort of know where you are. If you try to change things from the command line, if you ever get something messed up, then it can be hard to go and find that. So what I'll do is I'll step through these in slides and then go just show them in the core emulator. So in the base scenario, we're going to change UDP to use TCP in the N1 to N2 direction. So the first thing to do is to edit N2's bprc file so that it has a TCP induct, and just go ahead and listen on INRC. And then we're going to edit N1's bprc file so that we change the outduct that it uses to talk to N2 to use TCP instead of UDP. Then we're going to edit node 1's IPNRC file and change its plan so that it communicates with TCP when talking to N2. And then we can start or restart the scenario. And the way we're going to look at this is, we'll just TCP dump N2's ETH0 interface and confirm that it's got TCP and not UDP. So once you've done all that, testing and verifying, start bping from N1 to N2. So double click on the node on N1 and ping from IPN 1.3 to IPN 2.1, and then we can start Wireshark. And what you should see are UDP and TCP bundles both on 4556. And yet if you follow the instructions on the previous slide, you'll only see bundles moving from 2.4 to 4.1. Probably I'm going to have a look at these before I record the part where we go down and actually do this. I think these probably ought to be 1.3 and 2.1. So the instructions above left out a bit. The general framework for doing debugging and figuring out why an ion config isn't doing what you think it is, or should, figure out if you've got IP connectivity, and then I would try to say, are you sending? does the node that you think is sending actually transmitting, and are those bundles actually being emitted? And if so, then we can move on to, does the node that is receiving, that you think is receiving, actually getting those bundles in, ingesting them, and processing them. So one of the main tools for doing debugging and diagnostics is the ion.log file. So this is a bit of the ion.log file on node 1. So if you double click on node 1 and get a shell and just type cat ion.log, you should see something like this. So this says, okay, this is the I's here are informational. We're going along. This is all info. That's fine. We get down here and it says can't connect to TCP socket. Connection refused. And that seems bad. And we get that a couple of times. We do finally manage to connect to 10.022, but 10.002, no way. And another thing that we can do, there's a utility program called bpstats that if you run bpstats, it comes back with there's no output immediately to you at standard out. But what it does do is it causes Ion to dump information into the ion.log file. So it dumps information in this format into ion.log. Oops. That's talking about how many bundles were forwarded, how many were actually transmitted, how many were received, delivered, custody transfer, re-forwarded, and expired. And the numbers out here to the right are how many bundles of particular priorities. So priorities 0, 1, and 2, and then the plus is everybody. So we can look at that, and we can look in here at Wireshark, and we can see that, yay, verily, the ion, the information in the ion.log file looks like it was correct. In that 10.001 is trying to start a connection to 10.002, it sends a TCP SYN, and 10.002 tells 10.001, nope, go away, not going to happen. That's this reset TCP segment that's out here. And the magic bit was in N2's bprc file, we need to tell it that TCP is a protocol, and that it's, in particular, it's a protocol that it wants to use. So if you go into N2's bprc file and add a line that says add a protocol called TCP, and give it some valid numbers for segment size and overhead, and try again, then you should see success. Talk a little bit about running some of the ION admin commands interactively. Maybe I'm going to wait on this actually.